Yes, so I'm Trym, as Oscar just said, from the Oslo Metropolitan University, and I'm working with Stefano and Nichele as my supervisor on trying to create more sustainable computation. So as you know, like a lot of the cutting-edge AI systems that we're currently using, they're very energy intensive, both during training and during use. So we're really trying to look at other ways of creating computation that is a bit more energy efficient. Because of course the energy is often produced by fossil fuels, which is not great. So one system that can be more energy efficient is Cellular Automata. But even though Cellular Automata is pretty easy to, or has simple constructions, understanding them is pretty difficult. And since we're trying to engineer computational systems, we really need to have a kind of understanding of the CAs at a level where we can make informed choices concerning a series of parameters that will get us the kind of computations that we want in the end. And that's why we came up with this tool that we call the Canonical Computations and the related diagrams, which is what you see here, which was done with the help of Barbora Hudcova from Charles University, who also works on understanding the computational capacity of CA through algebraic methods. So that's kind of the overview. I'll do like a little bit of an introduction where we'll talk a little bit or do some semantic alignment and give some motivation. Then we'll talk about the canonical computation himself, and then we'll move on to sort of some anecdotal applications of these kind of diagrams. So first off, for a bit of semantic alignment, this method is generally applicable to most discrete systems, but I'll be talking specifically about elementary cellular automata. So just so we use the same kind of terminology, we have the cells, we have the configuration being the configuration of the different cells and their states. We have a transition rule, and we have a space-time diagram. So the main ingredients that we'll be working with. So the next question is, of course, like, why cellular automata to start with? Well, cellular automata can be Turing complete given the correct rules. So they can do basically the same thing as computers can. They're also very parallel because we can update all the cells at the same time. So we get some efficiency from that. For some things like the elementary cellular automata, the operations are on binary, which is cheaper than floating point operations of neural networks. And you can even implement them directly in hardware, which grants us even more energy efficiency. But there's also, of course, there's been like a lot of work trying to figure out how to use these computations. And we'll be working on specifically a method that's called reservoir computing. So let's talk a little bit about that. So reservoir computing is a pretty sort of general method of extracting computations from dynamical systems. So it's actually been done using a bucket of water and an acetite cat. My main line of work is using in vitro neural networks. Or you can use CA, as is in our case. So generally, this consists of sort of three main components. Most importantly, we have the reservoir itself, which, for example, can be a recurrent neural network. Importantly, we don't train this, which is where we get part of our energy efficiency from. You have an encoder, which translates your data into the states of the reservoir. And then you have a decoder, which consists of some method of reading out the data, and a linear machine learning method, for example, ridge regression or logistic regression, that translates the states of the reservoir into the desired output you want. For a bit more semantic alignment, this is like not like an autoencoder, because there was some confusion previously about this. It's just about encoding into reservoir states and decoding into desired outputs. So for reservoir computing with CA, or RECA for short, we simply use a CA as the reservoir. It would be great if this is all we needed to do, but finding the correct settings for all the different parameters is difficult. So a lot of the work that we're really trying to do is figuring out what different parameters gives us good RECA assistance. There's many things you can do. You can change how the encoder works, do encode into initial configuration over time, specifics about how you do those. You can change the readout method. So do you do the full space-time diagram? Do you just a subset of it as a rolling window? or which rules to use? And really one of the main issues here is that we don't really have like the good tools to figure this, to understand how the different parameter changes affects our computations. But given that we're working within this kind of reservoir computing framework, we had this kind of key insight. And that was that to the decoder, the CA is actually performing computations on the sets that are input instead of just simply on the space-time diagram itself. And that's actually what you're seeing here. These like set computations is what these diagrams represent, which gives us the information available to the decoder about the input. So this might be a little bit non-intuitive, so I'll explain this a little bit more in detail. So that we have some input set, the binary vectors of size 2, and we want to create a record system that does a classification on this input set. For example, we have class A is 1, 1 vector and 0, 1 vector, and class B is the rest. Now the decoder needs to learn weights that works across all of the different elements, right? So let's just compute all different space-time diagrams and take a look at how this kind of the basis for that extraction looks. So just go flip it for reasons that will become evident. And we compute the space-time diagrams for all the different inputs. Now, remember that the weights kind of work in relationship to the cells. So let's take a look at one particular spatial temporal location here and extract the cell states. That gives us this kind of column. And what we can see from this column is that the cell states are associated directly to each of the elements of the input set. Now, what this means is that what the CA has done is really create a binary partition on the input set, where each partition is mapped to the elements, to the state value of the cells. So this is what we call the canonical computation, because this is the information that is available for that cell to the decoder. Sure, good. And luckily for us, this this particular computation, or because we're doing binary, the Boolean function is the one that we were looking for to start with. So what the decoder needs to do here is simply set the weight to that cell to 1, its threshold to 0.5, and it has found the solution to the problem we gave it. And any location here, now it doesn't work, potentially computes different kind of computations. So here, for example, we have a different partition. And the next step was then to create this diagram, the canonical computation diagrams. And what you see here is basically the information flow within the CA. And what we've done is we've mapped out all the different kind of computations that's possible on the input set. And then we color-coded them in different gradients of blue. And we can, for example, then highlight the XOR computation here, which we can see sort of moving around the canonical computation diagram. And this is interesting enough itself, because now we can kind of think of the CA as performing computations on the, or the dynamics becomes dynamics on the computations instead of on the static states or space-time diagrams. So that would be interesting in of itself as a future analysis, but let's take a little look at some direct anecdotal, admittedly, and because we haven't gone to the part of systematically exploring this, but applications in reservoir computing. So for example, we can take a look at a number of canonical computations. So for a rule, this is again rule 45. If we take a close look here, we'll see that all the different colors are present in the diagrams, which means that if we use this, if we use the entire space-time diagram as input to the decoder, it is guaranteed to find any solution you want because all the solutions are there. So that might be a good idea, like rule 45, good under these circumstances, given this set, because we get everything. But what if we use a rolling window? That's one application that is often used in Reka as a readout. Now, in this case, the input set is a set of binary vectors of size 10, directly encoded into the initial condition, initial configuration of the CA of size 10. And because this computational space here is really huge, we've labeled the computations slightly differently. So we just label them in increasing gradient to blue as we discover them. And what we see here is really that rule 45 in this case just continuously produces new computations, at least for the time steps that we're doing, which we see by this gradient, which then becomes problematic because within the rolling window, the weights are static, and now they're always capturing new information continuously. And even though the information is like temporally stable, so within the window, it's always available, it may not be spatially stable. So remember, the weights are within the window, they're always static, even if they're rolling over the spaceline diagram. So for rule 45, again, the information is spatially jumping all around, even if it's could potentially be available within the window. Rule 30 is kind of similar, while rule 70, for example, under these particular conditions, has a transient and then rapidly goes into something that is spatially stable and more or less temporally stable, because it does flip a little bit. Now, rule 110 is a little bit interesting, because if we take a closer look at that, we can see that on the left here, it has these shifted cycles. So the information available to the decoder is actually, it's kind of like there, and it's in the same configuration, but it's shifted slightly, spatially shifted. And this gives us information for our Reka system, because here we can use a convolutional readout to deal with this issue. And similarly, or slightly differently, we can see how the encoder choices changes how the dynamics of the computation. Because even if this looks pretty similar on the right here, the left column of computations are actually slightly different. So in this case, we didn't get a perfect sort of shifted cycle, just simply because we increased the distance between the two encoded bits from 4 to 5. Similarly, for rule 151, for example, we can see here that the computation just entirely collapses if the distance is above 2. So for this particular rule, we know that never use that kind of distances. Similarly, we can see the same kind of effect for rule 18 with the size. Again, here we see a collapse of computations for the size of 15, which in a sense gives us like a very short memory, which could be beneficial in some cases, but also maybe not useful in other cases. So for summary, each of the spatial temporal locations in the CA are performing a canonical computation on the input set, given some encoder. And we can use these diagrams to visualize them. And to visualizing them gives us a tool to explore the effect of different kinds of parameters in the Reka system. And this may guide our choices for how we set up the different systems. So if you want to play around with this yourself, we have the GitHub code available. And if you want to take a look at some of the more diagrams we've computed, they're available from OSF, together with all the codes and some Jupyter notebooks too. And we'll include a paper link to this too here. So thank you. If there are any